Hello. We're going to cover a couple of topics out of section 4.1 of our calculus text. The part that I'm interested in is having to do with linear approximation. And the, the main idea that we're going to be talking about is thinking about a curved function and using points on a line to approximate y-coordinates on that curved function. And as I say here at the very top, our basic idea is that near the point of tangency, if I've got a tangent line on a function, then y-coordinates on the function can be closely approximated by taking y-coordinates on the tangent line. And I've got a picture below to try to illustrate this a little bit. So just to recall that if we have a function and a point on that function, we can write the equation of the tangent line to the curve at that point by using the point slope form of the line. Y minus the y coordinate equals the slope times x minus the x coordinate. And I could choose to rewrite that, and I think maybe we've done that somewhere earlier in the course, by adding f of a to both sides of the equation. And so if I move this over here, I get y equals f of a plus f prime of a times x minus a. So I can use this for y coordinates on the tangent line. And this, of course, is the expression for a y coordinate on the function. And what we see in this diagram below is that near the point of tangency, and so what I mean by that is if I go just a little bit out in either direction from the x coordinate at which the tangent line runs on this curve, that there's not much vertical distance. Think about the vertical distance here between points on the curve and points on the tangent line. There's not, that's a pretty small distance right there. And so what we've got is that the y-coordinate on the curve can be approximated by, that's what these squiggle symbols mean right here, approximately, can be approximated by y-coordinates on the tangent line. And so we might call this right here a linear approximation formula. So we're approximating the function with points on a line. But our author calls this expression right here, the right side of this approximation formula, it's called the linearization of the function at the point x equals a. So we're going to use L of x to stand for this formula up here. Before we get to some examples, I want to remind you how we calculate percentage error. If I've got an approximation that's using to estimate an actual value, I can get the percentage error by taking the difference between the approximation and the actual value, divided by the actual, take the absolute value of that, and multiply by 100%. We're going to do that in a couple of our examples. But first, let's just do a basic linearization of the function f of x equals 12 over x at x equals 2, and use it to approximate the value of the function at 2.1. So we want to remember that L of x, the linearization, is equal to the expression for y-coordinates on a tangent line. So we'll keep that in mind as we go through here. So in this particular case, f of x is 12 over x, and so f of 2, the y-coordinate, is going to be 12 over 2, or 6. the derivative we must calculate. So if I think about f of x as 12x to the negative 1, I can perhaps see reasonably quickly that f prime is negative 12x to the negative 2, or, if you prefer, negative 12 over x squared. So f prime of 2 is going to be negative 12 over 2 squared, which is going to wind up being negative 3. So this is my slope. This is the y-coordinate of my point. And so my linearization is going to be f of 2, which is 6, plus f prime of 2, which is negative 3, times x minus the x-coordinate, x minus 2. So this is my linearization formula for f of x equals 12 over x at x equals 2. So I can use that as for my linear approximation. F of 2.1 then is approximately L of 2.1. That's what the linear approximation formula says, which is going to be 6 minus 3 times 2.1 minus 2. And I get 5.7. Just for reference, the actual value, if I plug that into a calculator, f of 2.1 to several decimal places, 5.71428, and this is actually a repeating decimal, so this is the actual value of this. And so we can see that 5.7 isn't too bad of an approximation. My other two examples here involve calculating percentage error. And so my first question, approximate the square root of 36.5 using linearization. And then we're going to use our calculator to compute the percentage error. So at first glance, it doesn't seem like we've got a whole lot of information, but there's just enough here for me to figure out what f of x is and what the value of a is. And so those are the two things that we really need to know. So hopefully, if we take a second to look, it seems like we're talking about the square root of a number, so it makes sense that maybe f of x is the square root of x. And I need for a to be a number for which it's kind of easy to calculate the value of f of x. And so I'm going to claim that what I want here is for a to be 36. And the reason why I can see that's the case is that f of 36 is actually easy to compute. It's just 6. So that makes it pretty reasonable to think that a is going to be 36. So we find L of x. We've got the y-coordinate already, so I need f prime. Hopefully we're pretty good at this now, and we can see that the derivative of the square root of x is positive 1 over 2 root x. And so f prime of 36 is going to be 1 over 2 square root of 36, which is going to be 1/12. So my linearization is going to be my y-coordinate plus my slope times x minus the x-coordinate. So then my approximation, the square root of 36.5, is going to come from putting 36.5 into my linearization formula. And so I'm going to get 6 plus, this is a half. 1/12 times 1/2 is 1/24. And so I'm going to get 6 plus 1/24, and I'm going to round this to 6 decimal places. And so to 6 decimal places, that's 6.041667. And so this is the approximation. The actual, which I got from a calculator, to 6 decimal places again, is 6.041523. So here's my actual, here's my approximation. And so the percentage error is going to be the absolute value of my approximation minus my actual over my actual times 100%. And that turns out to be a really tiny number. As a percentage, I took 3 significant figures here, and I got 0.00238%. So that's a little over 2/1000ths of a percent. That means that our approximation is really pretty accurate. That's a very tiny error. But we expect, since we only moved a half of a unit away from 36, we should expect that the error is not going to be too large. Here's another example where the error is going to be a little bit bigger. Let's approximate the natural logarithm of 0.95 using linearization, and we'll calculate the percentage error again. Once again, I need to figure out what f of x and a are. Hopefully you're pretty okay with establishing that f of x is the natural logarithm function, and I'm going to take a to be 1, and that's because I know the natural log of 1 is equal to 0. It's easily evaluated. So here's f of 1. I need the derivative. The derivative of the natural logarithm function, the natural log of x, is 1 over x. So f prime of 1, my slope, is just 1. And so my linearization, in this case, is going to be 0 plus 1 times x minus the x-coordinate. And I can just rewrite this as x minus 1. So it's a really simple expression for the linearization this time. So that means the natural log of 0.95 is f of 0.95. That's approximately L of 0.95. 0.95 minus 1, negative 0.05. So this is my approximation. The actual from my calculator is negative 0.051293. Again, that's to 6 decimal places. And so my percentage error is going to be my approximation minus my actual over my actual. And remember, we're taking the absolute value of all that, multiplying by 100%, and this time I get about 2.521% error. So about 2.5% error this time in this approximation.